Hello everyone. Today we're going to be making a video about einsum, which is arguably one of the most underrated things you could ever use. And so right now, you might be wondering what einsum is. Well, the first part of the word einsum is ein, which comes from the word Einstein. So it's clearly when you merge a famous physicist with an orange blob, which honestly took less than a minute to make. And so I think that's all the explanation you need for this video. So, bye. Wait, hold on. You want an actual explanation of what einsum is, why we should use it, and examples of its use? Okay, here goes. Einsum, also referred to as Einstein summation notation, was invented by Einstein as an effective way to write long and complicated tensor operations into simple statements. But the way I like to think about it is as if somebody took every tensor operation they could think of and absolutely mashed them together into one big thing. And the really cool thing about einsum is that because of this, it is more optimized and generally can do operations faster and better than the traditional functions themselves. In addition, with a little bit of practice, it becomes easier to use einsum in your code and can even replace the traditional use of your ops. And so with that ado, let's talk about the general format of these statements. On the left-hand side, we have our matrices /tensors /vector operands to operate with. We represent these tensors by their dimensions, which I'll explain in the next slide. On the right side of the arrow, we have our output, which we again represent with dimensions. In this example, we represent a simple matrix multiplication using einsum. On the top, we are multiplying a 3x2 matrix with a 2x3 matrix, and the output dimension after multiplication will be a 3x3 matrix. Remember, the 2's cancel each other out, because the column of the first matrix and the row of the second matrix will get omitted from the output dimension. And with einsum, as mentioned before, we represent the matrix using its dimensions. We replace 3 with I, and 2 with j, and 3 from the column dimension of the second matrix with k. But you can replace these numbers with any other letter, and so we represent the first matrix with ij, the second matrix with jk, and our output matrix with ik. Our final notation is ij, jk equals ik. And the best thing about einsum is that it can do a lot more than just matrix multiplication. At least in most linear algebra libraries like TensorFlow, Numpy, and pytorch, you can do over a dozen operations all in one utility. These operations include the dot product, matrix multiplication, transposing, tensor contraction, trace, sum of all elements, Hadamard product, column sum, row sum, outer product, matrix vector multiplication, and batch matrix multiplication. Whew, that was a lot. Also, by the way, if you want to ignore dimensions, you can use ellipses to remove unnecessary ones. This is particularly useful when you want to discard parts of a tensor, or if you're multiplying with nested dimensions. First, let's start with matrix multiplication. We'll be illustrating the same process mentioned as our example, except in code. Okay, let's get started by creating our sample matrices, which will just contain placeholder values for the time being. I'll create 2 of them. A simple ones matrix with a shape of 3x2, and B, a simple ones matrix with a shape of 2x3. And so let me show you the traditional method first. We'll start by first declaring a variable, cmm, denoted as C matrix multiplied, and we'll be using NumPy's matrix multiplication function, which takes in 2 array values as input. Okay, but how do we do this in einsum? We'll then create a variable cein and use the np.einsum function. If you wish to use a library like TensorFlow or pytorch, you can simply replace the np with the abbreviation for those libraries. Anyway, we next have to make our einsum equation. To do this, let's try to figure out what we want to do. Okay, so we have a matrix with dimension 3x2 and a matrix B with dimensions 2x3. and we have to represent those dimensions using variable names, as shown in the example before. So I'll represent the 3 by 2 matrix with ij, and the 2 by 3 matrix with jk. Remember, I'm separating the values with commas to differentiate them, just to let NumPy know that the ij matrix is different from the jk matrix. Right. Next, we have to think of what our output will be. In our matrix multiplication, our output will be a 3 by 3 matrix, and when getting the associated variable names, it'll be an I, the row of the first matrix, by k, the column of the second matrix. This is our einsum equation. We then pass in our two arrays, a and b, to the einsum function. Let's now print these outputs to see if we did it correctly. And now let's run the program, and we'll see that our outputs for each function are the same. Likewise, we can also do a matrix vector multiplication as well. Let's start by declaring our matrix A, but this time we'll initialize B to be a vector. We'll do this by making a numpy 1s, and we'll set the shape to 1 dimension, just 3, comma. Okay. We can store the traditional output in a new variable called c_mv, which symbolizes C matrix vector multiplication, and we can again use the matmul function to multiply these together. As a proof of concept, we can use the same variable cin to denote the output of the matrix vector multiplication. And, like the traditional matmul, you do not need to change much to multiply a matrix with a vector. We can again represent the first matrix with ij, like we did before, but we only represent the second matrix with j, as it is one-dimensional only, and it is of length 3, which is what the j variable is supposed to represent. Our output dimension will just be I, because the two j's, which is the column of the first matrix and the, row of the vector, will cancel out. And as usual, we can pass our variables ab to the function and print out the results. And as expected, the results will be the same. We can also do an element-wise multiplication, which the scientists call a Hadamard product. I know, very sciencey. With element-wise multiplication, we declare two matrices with the same dimensions, and we can multiply them by just using the Python multiply operator. With einsum, we represent both matrices with ij, as they both have the same dimension, and we represent our output matrix with ij as well, because it will also have the same dimension as the two input matrices. We then pass in our matrices and print the outputs. Let's see if it works. Yes, it does. Okay, let's talk about batch matrix multiplication. Honestly, it's so similar to matrix multiplication that I'm not going to restart this tutorial. I'll just show you the little modifications which you have to make. And so in this code example, you can clearly see that I've added batch dimensions to both the matrices. And as you can see, I don't have to change anything with my matrix multiplication function. But with einsum, we kind of do, unfortunately. But it's really not that big of a change. All we do is we add another batch dimension over here, as you can see on all three matrices, because our first two input matrices have the batch dimension, and so should our output. Right. And so we just keep our input matrices and print them out, and as expected, we should get the same output. If I scroll down, you will see that both of these are the same. Okay, so let's talk about how we can find the sum of all elements in an array using traditional NumPy as well as this newer einsum approach. We'll first start by declaring a matrix A, and we'll just make it a square matrix 2 by 2 dimensions. Okay, great. Now, let's talk about what we're going to do with the traditional method. And I said this is something which isn't as obvious as something like matrix multiplication. I'll just be creating a variable c_add to represent, the traditional method. And I'll be using numpy sum. But here's the part that gets a little bit not obvious, I guess. We're going to be using numpy.concatenate, and we're going to, basically what this does is it's going to flatten all the elements in this array. And I think I assume because we're just concatenating it, this approach only really works for two-dimensional arrays. You might have to do something like a numpy.reshape, some kind of special reshape, if you want to do this properly. But anyways, now let's talk about how we can do this with einsum. And I think this is a really good advantage of einsum. It really simplifies the workflow here. We're going to create a variable ein, right? And we're going to use numpy's einsum. And so let's talk about what our structure is going to be. Well, we know we only have one matrix, and it's two dimensions, so we can represent it with ij, I being the first two, j being the second one. But then you might be wondering, hey, what comes after, right? The sum is going to be a scalar value. What do we put as a scalar? What variable do we use? How do we represent it as a dimension when a scalar is 0 dimensions? Well, we put nothing. We just put the equal sign, and we don't put anything in the end. And when that happens, we basically let einsum know that our output will be in the form of a scalar. Okay, and we're going to do that as usual. We're going to pass our array and pass our print statements, and let's just check if this works. And it does. Hoo-hoo. Sync. Okay, transposing is another instance where einsum really shines compared to its counterpart. It seems a lot more natural and seamless than the traditional approach. And so let's demonstrate. I'm going to just create a little array A, and this will be a numpy ones array with dimension 3 by 2. Those are like the two smallest, most intuitive values, I guess, to represent a matrix. And so we're going to make our traditional variable c_t, c transpose. We're going to use numpy's transpose function and just pass our array in. And with let's talk about what we're going to do with einsum. We're going to just declare our variable ein, and we're going to use numpy's einsum, right? And so let's think about this. Our array A, its dimensions, it has two unique dimensions, and so we're going to represent it with ij, right? And with transposing, our dimensions are flipped. So instead of ij, our output will be ji. And that's really the way I like to think about it. And so we'll pass our array in, and let's just check our outputs. I'm just going to print A as a reference, and our transposed traditional and transposed Einstein to kind of validate if it works. As you can see, this is our original array, and when it's transposed, in a sense, we kind of rotate the array. We flip the dimensions around, and as you can see, both of them are rotated the same way. So let's talk about how we can do column and row sums. If you don't know what that means, don't worry, I'll explain it. So it's basically when you aggregate the sums along a certain column or row. So for example, for a column sum, you would sum up the elements in each row, and then in the end you would have like a vector or a list with the sums for each row, but you have a column number of elements. And that's the way I like to think about it. And so to do this, let's first start by declaring a variable A, and we're going to make it a simple generic array with the shape of 3 by 4. And let's learn how we do this in NumPy. We're going to use NumPy sum, and we're going to use the A function. We're going to use A, and we're going to do it on the 0th axis, which means we're going to sum the rows instead of the columns. And for einsum, again, I really think it's a lot more intuitive in einsum than in NumPy. Sometimes I get confused by the axis. Anyways, with einsum, we are going to use the simple NumPy einsum. And here, we have our original array, ij, which is the 3 by 4. We have two distinct dimensions, so, I and j. And in the end, we're just going to have the column dimension, which is j, right? And that's basically the reasoning for this equation. We're going to pass in our array as usual and print out the values. And in the end, our results should be the same. Okay, let's talk about how we can do the most, I'd say, quintessential operation in linear algebra, the dot product. We'll first start by creating two vectors, A and B, which just have 3 elements in them. And let's talk about the traditional method. I'm sure you might know this. We're going to create a c.dot variable, which uses the numpy dot function, which takes the dot product, and we take a and b as input. And for einsum, it's just as easy, to be honest with you. We're going to use numpy's einsum, and let's think again. How can we represent a and b's dimension? Well, a can be represented by I, and b can also be represented by I, because a and b only have one dimension because they're vectors, and they're both the same size, I guess, so we can use I. So I for a and I for b. And let's talk about our output. Remember, the dot product is a scalar. What we do is we do an element-wise multiplication between the two vectors and sum them up, I guess. Obviously, the methodology for the dot product is a little bit more complicated, but that's basically the gist of how you would do it. And because it's a scalar, we do not include anything on the other side of our einsum output because it's a scalar. And we can just do the usual. We just add our two arrays and print out our values. And when we click the run button, they both work. Both the values are the same. The next thing we're going to do is called the outer product. And if you don't know about the outer product, I think it's personally pretty interesting to learn about, and I think you should learn about what it is. And if you know what it is, just stay tuned for a couple seconds. So let's talk about what it means. So let's say we have two vectors of different shapes, okay? One vector has 3 elements, one has 2 elements, for example. And what we do with the outer product is we say 3 outer product 2. We'll then get a matrix with dimensions 3 by 2. And that's basically the gist of how it works. And so let me show you how we do this in code. Let's first declare our two matrices. We're going to create a vector with length 3 as well as a vector with length 2. And to do this in NumPy, traditionally, we're going to create this variable, and we're going to use NumPy's outer function, which takes in these two arrays as input. And let's talk about how we would do this with einsum. We're going to use NumPy einsum. And first, we have two different vectors of two different dimensions, right? But each one only has one dimension. Vector is a rank 1 tensor. So for A, I'm going to represent it with I, and with B, because it's different length, we're going to represent that with J. And with an outer product, we're going to get a matrix, in this case 3 by 2, or in a more generalized form that we can give to einsum, I by J. And we're going to pass our two matrices as input. And so now let's just print out the responses and let's see if they are the same. As you can see, yes, they clearly are. We have the trace. And the trace is basically when you take the sum of all the elements on the matrix diagonal. And I think it has some practical uses when it comes to matrix calculus, and so you'll have to check that yourself and see. But whatever your use case, einsum will be a great way to deploy this operation. So first, let's create an array A, and we're going to just create a rectangular matrix 3 by 3, because it's only those kinds of matrices which have that kind of diagonal, right? And so we're going to use NumPy's trace utility, and we're going to get A. We're going to take A as input. Now let's see how we would do it with einsum. What we do is, it's pretty simple, and it looks a little bit confusing at first, and honestly it kind of confused me too. We basically represent this 2D matrix, because it's rectangular, we say I. And if you're kind of confused, hey, where is our sum part, right? Because this trace is a scalar, we should at least have that arrow. But I think this is some kind of exception to the einsum paradigm, I guess, the einsum general rule set. So I think it's kind of something which you have to memorize. So anyways, we have to take in this A, which is our matrix, as input, and let's just see what happens. And as you can see, these two are the same, and it's logically 3. It's a 3 by 3 array. The sum of the diagonal is 3. We've saved the best for last, and by best, I kind of mean the hardest to, I'd say, intuitively understand. This is called tensor contraction, and the way I like to describe it is, when we kind of want to discard some of the dimensions and aggregate them. So it's kind of like a row or column sum, except in, I'd say, a higher dimensional space. I'd say that's the way I like to describe it. And in this example, you'd see that I actually included these arrays first. In this example, we have a 3x4x2 array and a 4x3x6 array. And using the tensordot in a special way, where we specify our axes, we can get an output array which is 2x6. So essentially, we kind of ignore these first two dimensions. And that's basically the gist of what a tensordot is. Okay, so the way we do it traditionally in NumPy is we use a np.tensordot, and we pass in our arrays, but then we also have to pass this axes parameter. And this axes basically kind of tells what dimensions to, in a sense, cancel out and ignore each other. For example, this first, we ignore the first and the 0th index of the first A, as well as the 0th and first index of B. And I'd say, in a sense, we kind of cancel these two out using like a matrix multiplication sort of thing. And so now let's talk about how we would do this in einsum. We're going to create a new variable for einsum, and we're going to use einsum. And we basically have to first represent these two matrices. And this one is a ijk. The first A is an ijk. 3 is I, 4 is j, and 2 is k. And B is j for 4, I for 3, and 6 for L. We're going to use ijk, comma jil. And we want our output to be a 2x6. So our output will be a k by L. And so we pass in our arrays. It's pretty routine, getting pretty tedious at this point. And we print out the values. And they're the same. Woohoo! We are finally done with this great lesson on einsum. I really hoped you liked the video, and I really hope that you'll like, subscribe, and share this video to get the algorithm running. Thank you.